Hello all, and welcome to your first official lesson of Geometry Summer 2020. Um, we are going to be talking about a lot of definitions today. So this is section 1.1. Um, you can't go through geometry without understanding the definitions and the specific notation. Because when you're discussing properties and discussing postulates and discussing proofs, you need to be able to have a universal language that we can all have, so we can all have the same discussion. Okay, so we're doing a lot of just talking about important terms. Now, some of these terms might seem that you might have seen before, but they're all very important. So I suggest taking notes, or you could also follow along on your actual computer or on your actual Pearson website so that you can go at your own pace. I'm going to try to go a little slow. I'll leave each slide up a little bit. I'll talk about the important parts of each slide, and then I'm going to move on. And the best thing about this type of learning is that you can always pause me and write things down if you would like to. So we're starting here with just three terms that we'll talk about. The first is a point. A point is just a single point. It has a location, but it has no size. Okay, so it looks like this, just a point. It'll be labeled, we call this point P, and you just use a single letter to denote a single point. Okay, a line is an infinite number of points on a straight path that extends in two opposite directions, has no end, and it has no thickness. Like here, we have point A and point B on line L. And so I might look at this and I might call it line L. You might look at this and you might call it line AB. If you're using this notation, which you'll see a lot, you'll see the arrows going in both directions above the AB. That tells me that it is a line and not a line segment. So we have a point, we have a line, and then we have a plane. Okay, a plane is an infinite number of points on a flat surface. Think of the desk that you are currently sitting at right now. That desk is a flat surface. That could be a plane. A plane could be defined by a single letter. So like this is plane M. Or it could be defined by 3 points on that plane. So it could be plane XYZ. The reason why it cannot be defined as just 2 points is because 2 points make a line. So I can call this line XY, but this is plane XYZ. So geometry is full of points, lines, and planes. Okay, and then we have some more definitions. If this loads, here we go. So we have what's also called a line segment. So I was telling you a line goes off in two directions infinitely. A line segment is part of a line that consists of 2 points that are called the endpoints. So here we have a line segment AB. We'll be dealing a lot with line segments throughout the year. And when you make that notation, you don't put the arrows in both directions. So you have line AB with a bar above it. A ray looks like a line, except it goes off only in one direction and has an endpoint. So the endpoint here is M, and it goes off in the direction of N, and that's why the notation is MN with a ray above MN pointing in the direction of N, because it's telling me that this ray is going off into direction N. Okay. So here we have opposite rays, are rays with the same endpoint on the same line. So this could be line SU. It could be line ST. But we're talking about the ray itself. The ray is TS going towards S, or it could be TU going towards U, and they are opposite rays going in opposite directions with the same endpoint, and therefore they're on the same line. Okay, and we also have an angle. So here is my angle. It's formed by two rays that in each ray is a side of an angle, and the common endpoint is called the vertex of the angle. So Q is the vertex of this angle. We can denote this angle as angle Q. We can denote this angle as angle PQR. So PQR, as long as the middle letter is the vertex of the angle. Or we can denote this as angle 2, because there's a 2 on the inside. So there are many ways to write angles. Sometimes it's easier to write it one way or the other, or you may have to label some things throughout your work to then talk about them. Okay? All right. So we're going to be talking about how to find the length of a segment. This may seem very intuitive, but if we're looking at essentially a number line, okay, and we have points on our line, A, B, C, and D, and we want to find the length of CD. So if I'm physically looking at the number line, I can go ahead and just count 1, 2, 3. Okay, so the length of CD is 3. Now the important part of this topic is not that you can count from 1 to 4, is that you know how to write this as an answer. So line segment CD is written as CD with a bar above it. However, when we start talking about measurements, okay, you don't have to put the bar above it. So you'll see that CD equals 3. So now I'm saying, okay, I'm putting it into an equation. CD equals 3. So when you go from just talking about line segment CD to then going into an actual measurement of line segment CD, you can drop the bar above it and say CD equals 3. Okay? You can also just write it in a sentence, but when you're going back into the sentence, you have to put the bar back above CD. So the only time you'd lose the bar above CD or the line above CD is when you're talking about a specific measurement in an equation. So CD equals 3 versus line segment CD is 3. You'll see this notation has the bar above it. Okay. So a postulate is assumed to be right, assumed to be correct. It's things that you can intuitively, everyone should know. Okay, so in this case, this first postulate we're talking about is called the ruler postulate. Okay, the ruler postulate just says that every point on a line can be paired with a unique real number. Okay, it's the coordinate. You have looked at coordinate geometry before, and back in your Algebra 1 class or Algebra 2 class, where you had an X and a Y value, and that was your point. But if we're looking at just a single line on a ruler, now we are looking at a single point. So therefore, the coordinate of X is 3, the coordinate of Y is 7, and so forth. So that's called the ruler postulate. It's just that every single number can be matched up, every single point can be matched up with a number. The distance between 2 points. So again, we can always just count the distance, but obviously things are going to get more complicated than that. In order to find the distance between 2 points, we got to think about how distance is always positive. So how do we make sure distance is always positive? Well, we could always do the bigger number minus the smaller number. So 7 minus 3, so the distance between X and Y is 4. Or we can talk about absolute value. Absolute value essentially is distance. And that's why absolute value always makes your number positive, because distance is always positive. Okay? Direction is when you get positives and negatives. But here we're talking about just distance. So we could take the absolute value of 7 minus 3, which is 4, or the absolute value of 3 minus 7. 3 minus 7 is negative 4, but the absolute value of that is still 4. So therefore, the distance on a line is just the absolute value of their 2 points subtracted. Okay, and we'll go through a quick example. It says to use the ruler postulate to find the coordinates of K and L. So point K is at 12, point L is at 16, and we're finding the distance between these two. we would do 16 minus 12 is 4, or 12 minus 16, and the absolute value of that is also 4. Therefore, the distance between K and L is 4 units. The segment addition postulate. So this is a major postulate that will be used especially during our unit on proofs. The segment addition postulate says that if you were to add two pieces of a segment, you would get the whole segment. For example, if I have segment AB and segment BC, so when I add AB and BC, I get AC. Now, the segment addition postulate, you'll notice that there's no bars above AB and BC. Again, when you're putting things into an equation, you no longer need the bar. Okay? So AB, we know, is going to be a line segment and not a line. That's because AB is a number. A line will have a distance of infinites because it goes off infinitely. A line segment has a finite distance. So we have AB plus BC equals AC. Here's a little diagram over here you can play with on your screen as well. So you'll see I have point A, point B, point C. And it gives you the distance from A to B is 5. The distance from B to C is 5. When you add them together, you get 10. Now I can move B around. So now AB is 4, BC is 6, but AC is still 10. AC has not changed no matter where B is, because I'm just moving the two segments around, but the total distance AC is the same. The only time that would change is if I was to move C. Because now C is getting bigger, and I move C all the way out to here. Okay. Now the distance between A and C is 12. AB is 7.2 and BC is 4.8. 7.2 plus 4.8 is 12. So the segment addition postulate just says that if you were to add two parts of the segment, you would get the entire segment. Let's do an example. Okay, so I have points F, G, and H, and they're collinear. Another word we haven't quite seen yet. Collinear just means points on the same line. Okay, if they're collinear, that means that they're all on the same line. Co meaning same, linear meaning line, collinear. So F, G, and H are collinear. You'll see the distance between F, G is 3x minus 1, and the distance between G, H is 2x plus 2. Up here, it tells us that GH is 16. It wants us to find FH. So, since they're collinear, we know they're on the same line. I first need to figure out what x is. Since GH is equal to 2x plus 2, and I know that GH is 16, I'm going to set 2x plus 2 equal to 16 and solve for x. I got x is equal to 7. Since x is equal to 7, I can go ahead and substitute 7 back in to find FH. Okay, so you can do it two ways. You could input this value back into here to find FG, or you can say that FH is FG plus GH, and when you add these two together, 3x plus 2x is 5x, negative 1 plus 2 is 1. So when you add FG plus GH, you get 5x plus 1. You can substitute 7 back in, and you get that FH is 36. So segment addition postulate. Okay. So we're not just going to be looking at segments, we'll be looking at angles as well. So next we have a protractor postulate. Again, a postulate is something that is assumed to be right. Okay, it's basic knowledge that we assume is right. We can use these postulates to eventually prove theorems and prove triangles, congruency, similarities. So we're going to be using these postulates a lot. So even though they may seem basic, we need to understand what they're saying. So in a protractor postulate, we have ray BA, and point C that's not on BA. Okay, so here's ray BA, here's point C, okay, and it can be given a unique real number from 0 to 180 can be assigned to ray BC, okay, and 0 is assigned to BA, and we have this. Okay, it's a protractor, and this is how we read angles. So looking at this, if I was looking at angle ABC, angle ABC is 60 degrees. Okay, start is going from 0 and up to 60. Whereas angle CBD is 120 degrees because it's starting at 0 and goes all the way around to 120. Okay, it's a protractor postulate. Okay, we're going to be using protractors a little bit in class. A lot of straight edges, a lot of compasses. So here we're just looking for various angles. So the measure of angle BEC. So here's BEC. That's strange because BEC doesn't start at 0. So how do we go about finding angle BEC? Well, since EA lines up at 0, so here's EA, we're going to use the top scale for all of the other rays in the figure because it's going this way. Okay? By the protractor postulate, real numbers are assigned to EB and EC. So here's EB and here's EC. Okay? So 47 is assigned to EB. So EB is here. It's kind of hard to see. Here's 45. Here's 50. So we'll say, yeah, 47 is assigned to EB. And 105 is assigned to EC. So here's EC. Here's 100, 110. So 105 is given to ray EC. If we were to subtract these two rays, 105 minus 47, you would get the angle in between, right? So AEC is 105 degrees, AEB is 47 degrees. If you subtract the big angle and the small angle, you get what's left inside. Of course, angles have to be positive, so we gotta do the absolute value. Okay? So it's just the big angle minus the small angle in here. Okay. And one of our last postulates that we're going to talk about today is called the angle addition postulate. Very much like the segment addition postulate. When you add two pieces of an angle together, you get the whole angle. For looking at this picture right here, I have angle ABD, that's this small guy here, and angle DBC, that's this small guy up here. And when I add these two angles together, I get the whole angle ABC. So this is the angle addition postulate, which is the same thing as the segment addition postulate, but just looking at angles. We can play around with the angles over here. So here I have point B, point C, point A, point D. You'll see that each of these small angles is 30. The whole angle is 60, but I can move point C around to change the small angles, but angle ABD is not changing. It's still 60. Okay? I could also change angle A, and now I'm changing angle ABD because ABC is 65, CBD is 31. You add them together, you get 96. Okay? So again, you can play around with this on your end if you would like to, but this is the angle addition postulate. Okay. Long example here. Let's talk about congruency as well. Okay, congruent, as many of you might know, kind of means equal to. Okay, there is a big difference between congruent and equals. However, when we equal something, we equal a value. For example, 4 equals 4. Okay. If we are talking about line segment AB, AB could equal 4. Whereas congruent means that line segment AB is congruent to line segment CD. We don't know the length of AB or the length of CD, but we know they're congruent. We denote that by putting a tick mark. So here's AB, here's CD. One tick mark on each says, hey, these two are equal. Or two tick marks. They have to have the same number. It could be 5 tick marks. However many tick marks you want to use, that denotes congruency, which essentially says their distances are equal. You can do the same thing for angles. So here's angle TUV and angle XYZ, and these two angles are congruent because they have the same amount of tick marks, 1 tick mark each, or 2 tick marks each. Therefore, they are congruent angles. So we can have congruent line segments, we can have congruent angles. Congruent means they are the same measurement. Sometimes we'll know the measurement, sometimes we won't. Okay? There are some properties of equality that have equivalent versions for congruence. Okay? So these 3 properties are going to be used a lot. So we have first the reflexive property. The reflexive property says that AB is congruent to AB. So here, this line, AB, is congruent to itself. Well, that makes sense. Okay, it has to be congruent to itself. We also can use it in angles. Angle A is congruent to itself, angle A. Duh. It might seem silly to write it, but it's going to be very helpful when we're proving things congruent. Okay, so that's called the reflexive property of congruence. The symmetric property of congruence says that if, for example, if AB is congruent to CD, then that means CD is congruent to AB. If angle A is congruent to angle B, then that means angle B is congruent to angle A. Okay, that is the symmetric property. If I'm congruent to you, then you're congruent to me. Okay, and finally, the transitive property of congruence. If line segment AB is congruent to CD, and CD is congruent to EF, by the transitive property, AB must be congruent to EF. Right? If I'm congruent to Jim and Jim is congruent to Bob, then I must be congruent to Bob because we're all the same. You can use this property for angles as well. If angle A is congruent to angle B and angle B is congruent to angle C, then that means that by the transitive property, angle A is congruent to angle C. Okay? Now I want to just talk about notation for a second. I'm going to leave this screen and bring up my notepad here. Okay. Let's talk briefly about congruency and how you write it. If we're talking about a value, for example, there we go. Okay. Talking about line segment AB. AB can be congruent. Congruent is an equal sign with a little squiggle. Congruent to CD. Okay. But if we're talking about a measurement, okay, we could say that AB is equal to 4. Okay. We can say that CD is also equal to 4 because these two lines are congruent. So because this statement is made, and I said, oh, AB is equal to 4, so let's just draw it over here. Here's A, here's B, here's C, and D. So I said, oh, this is 4. And because this is 4, because that's 4, then this is also equal to 4 because they are congruent. Okay? We do not. We don't write this. A, B is congruent to 4. We don't write that. Nope. Okay? When we're talking about equaling a number or equaling a value, we talk about equal. If we're talking about two things that are the same, they are congruent. Okay? So the reason why it's so different is because if I said my left arm is congruent to my right arm, the only information that gives you is that my left arm and right arm are the same. But if I tell you my left arm is 3 feet and my right arm is 3 feet, I'm now giving you numerical values for my left and right arm. Okay, so those would be equals versus congruent. Okay. This notation will be important as we move forward. Okay, so again, AB is congruent to CD versus this says AB equals 4 and CD equals 4 because they are all congruent. Right? So we learned what seems to be some basic postulates, but they're very important. Okay, we have the angle addition postulate, we have the segment addition postulate, we have we have the ruler postulate, the protractor postulate, and we have the reflexive property, the transitive property. These are all very important terms that we're going to need. So again, this was a lot about vocabulary, but we're going to be using this vocabulary, so this should be something that you should have written down so that you can refer to these postulate names and property names, so that when we're discussing proofs and we're discussing more in-depth topics, we can use the correct terms universally. All right. So this wasn't the most exciting lesson, I understand, but it's a very important lesson in the foundation of geometry. All right. Your next task will be to complete the 1.1 additional practice to make sure you understand fully the various properties. All right. We'll talk soon.